Good morning, students. In this lecturette, I'm going to cover the motivation behind learning MIPS assembly programming. So far in ECPE 170, you have programmed with high-level programming languages like C and Python. Now it's time for us to shift gears and start learning how to code in low-level programming languages. Specifically, we are going to use the MIPS assembly. So this lecturette covers the motivation behind it, and I'm going to show you why MIPS is important for computer scientists, computer engineers, and electrical engineers in their respective careers. Before we move any further, let's go over our lab schedule. So these are your remaining labs that are due. So lab 10 is due April the 11th at 5 a.m. Lab 11 is due April the 18th, and lab 12 is due April the 29th. And for the rest of this week, this is our agenda. So I'm going to post lecturettes one after the other. This one is lecturette number 1, which covers motivation behind MIPS. Lecturette 2 is going to cover MIPS arithmetic instructions and branching instructions, which are going to help you convert codes, snippets such as if-else statements and while loops, for loops, etc. to MIPS. Then lecture 3 covers MIPS memory instructions, where you will learn how to declare memory variables and how to declare arrays and how to manipulate arrays and so on and so forth. So the person of the day today is John Koch. Now he is considered as one of the greatest pioneers of computer architecture, and in fact he's called the father of RISC architecture. Now the RISC stands for Reduced Instruction Set Computing. I'm going to go into RISC architecture in detail a little bit after some time. So I'm going to stop talking about RISC right now and focus a little bit more about John Koch. So he's the winner of ACM Turing Award, which is considered as the Nobel Prize in computing. Unfortunately, we do not have Nobel Prize for computing, a dedicated Nobel Prize for computing, but Turing Award is as close as to that. The second person of the day today is John Hennessy. Computer engineers in this class may read one of the books written by John Hennessy and David Patterson called Computer Organization, and there are 2 volumes usually. One of them is the software approach and the other one is the hardware approach. So in these 2 books, both John Hennessy and David Patterson have used the RISC architecture, MIPS, and explained how your processor is typically constructed. So John Hennessy was responsible for popularizing RISC architecture in early 1980s, and he founded MIPS Computer Systems in 1984. Since then, I think some 6 to 7 years ago, MIPS Computer Systems was sold to some other company. John Hennessy also served as the president of Stanford University, and he retired in 2016. So far, this is how our class's approach has been to programming. You students as humans, you typically wrote your C code using one of your favorite editors such as Gedit or Vim, and then you compiled your code using GCC. Now, GCC was responsible to check the syntax of your written code, and then if everything was okay, it generated an intermediate assembly code. And then your compiler optimized this assembly code and then subsequently produced object files or binary code. And if you had multiple C files, then you had multiple object files. Your compiler GCC was responsible to link these files together and create a final executable. And then you executed that executable using commands like /a.out or / the name of the executable that you may have given, followed by some command line arguments. But now, for the remainder of our class, our focus is going to be on assembly code. In that way, we'll be a little bit more closer to the underlying computer architecture. So we will write our assembly code, and then assembler is going to generate object files for us, which is then going to ultimately generate an executable. Now, we will be using a special simulator called Qt-SPIM in order to simulate an assembly code. Now, what I'm going to do is I'm going to ask you a question, and you are going to take about 15 seconds of your time to write that answer down on a piece of paper. Now my question is, why are we humans as programmers moving a little bit more close to the computer architecture by writing assembly code? I repeat, why we humans as programmers are moving a little bit more closer to the underlying computer architecture by writing assembly code. What could be the benefits? take about 15 seconds of your time, take a piece of paper and write it down. You can also pause your video at this point if you would like. Otherwise, we are going to proceed ahead after 15 seconds, starting now. So once this hourglass disappears, we'll proceed ahead. Okay, so I hope you had some time to write down key points as to why we humans as programmers would possibly benefit or could possibly benefit by moving a little bit more close to the underlying computer architecture. If you did not get enough time to write it, it's okay. The goal was to make this video a little bit more interactive rather than just I talking. So let's talk about MIPS. So MIPS stands for microprocessor without interlocked pipeline stages. Now, rarely we use this entire full form for MIPS, and we just call MIPS architecture as just MIPS architecture. Now, this was a family of computers that was first introduced in 1981 by John Hennessy and team. So MIPS products are prevalent in several markets. For instance, you have embedded devices, you have Cisco's routers, you have cable boxes that have MIPS products in them, you have MIPS processors controlling these devices. Then gaming and entertainment have also used MIPS products. For example, the earlier PlayStation devices, PlayStation 1 and PlayStation 2, had MIPS architecture in it. Subsequent PlayStations had IBM Cell and some other architectures, but the earlier versions of PlayStation had MIPS. Computers, not so much. There were some earlier workstations back in 1980s that used MIPS processors such as SGI, DEC, and NEC workstations, but not quite a whole lot. One of the popular examples of a MIPS product is NASA's New Horizons probe, which was launched in January 2006. Now, it featured MIPS Mongoose V chip, which clocked at 12 megahertz, and it was radiation hardened, meaning that it could sustain heavy radiation out in the space, and it was based on MIPS R3000. So let's talk about RISC, what RISC actually means. So RISC, it stands for Reduced Instruction Set Computing. Now what it essentially means is that for a given processor, you will have a small set of instructions with which you have to program that processor. Now, because you have a very small set of instructions, your underlying hardware is going to be small and therefore it can be clocked faster. Now, RISC is in contrasting with another architecture called CISC architecture, C-I-S-C, which stands for Complex Instruction Set Computing, which has some instructions that are used for accomplishing complex tasks. Now, if you were to accomplish those complex tasks using RISC, you would have to use very simple instructions. Now, because this architecture is a little bit more complex, it has more complex instructions, correspondingly, the underlying hardware also tends to be a little bit more complex. And therefore, CISC architectures may run a little bit slowly. They may be clocked a little bit slowly, a little bit at a slower speed versus the RISC architecture. So with respect to the RISC architecture, we'll be using MIPS 32. And what does it mean? Well, in MIPS 32, we are going to define a word as a register that has size which is equal to 32 bits. So frequently, we'll be talking in terms of word when we code in assembly programming. So we'll be using register size of one word, meaning a register size is going to be equal to 32 bits. And all of the data is going to be processed with respect to this one word. Now, the newer architecture of MIPS, such as MIPS 64, has 64-bit registers, but we are not going to touch that because for learning purposes, we are going to focus on 32-bit architecture. Okay, so I would like to recall one of the quotes said by the great Donald Knuth. And that quote is as follows. So people who are more than casually interested in computers should have at least some idea of what the underlying hardware is like. Otherwise, the programs they write will be pretty weird. Now, this particular statement is actually our motivation to do MIPS labs. Here's what I would like for you guys to do next. Just think about how MIPS could potentially affect your career ahead. You're trying to use a programming language that is really very close to the underlying architecture. Why could or how could a career involving writing assembly codes potentially impact you? So think about it for some time. Let's take 15 seconds of your time, and then we are going to move further ahead once the sandglass disappears. So how MIPS programming or how assembly programming could create an impactful career for you. Okay, so I hope you had some time to write it down. Alternatively, you could pause the video at this point and try to write it down as well, and then we can move ahead. So you can go through this video at your own pace. That's absolutely okay. So let's moving on. Let's move on and look into some other aspects. Okay, so let me tell you how could these different students could possibly benefit from MIPS programming in their toolbox. So let's consider computer science track, for example. Now, as computer scientists, if you are able to write your code in MIPS assembly or in any assembly language in general, you'll be able to understand how the processor works. In addition, you'll be able to further optimize your program as well. Now, carefully recall what a typical compiler does. Let's take, for example, what the GCC compiler does. If you recall the functionality of a GCC compiler, it not only checks for the syntax, but it also generates an intermediate assembly code, which it further optimizes so that your program runs faster on the underlying processor. So it's the compiler that is optimizing the assembly code. And compiler designers are the one that are writing compilers in such a way that they have the capability to optimize the assembly code. So in future, if you are interested in a lucrative career of being a compiler designer, a sound understanding of assembly language programming will be quite useful for you. Let's talk about computer engineers. Now, as computer engineers, you may be writing some fast performing codes for microcontrollers that are going for, let's say, deep space missions, for example. So an intimate understanding of assembly programming, how to optimize it, can really affect how the space probe or whatever space device that you're sending outside is functioning. So in fact, there's a whole story about Apollo missions. So Apollo missions were actually written in an assembly language, and those were called AGS, if I am not wrong. But I can check that again. So in one of the missions, something happened to the assembly code, but the personnel that were on space mission, they were able to quickly rectify this problem by looking into their actual assembly code and fix it, and thereby making sure that nothing inadvertent happening. So there you go. So assembly programming can also impact the careers of computer engineers. Computer engineers that can write good assembly codes can find jobs pertaining to real-time operating systems and writing codes for microcontrollers that are deployed out there on the field. So in addition, let's say that you're also interested in a career as a computer architect, then having a sound knowledge of assembly programming will be quite useful, because then you will understand how the processor is going to implement all these different assembly instructions, and how the processor knows which instruction to process and which data to process. So if you are looking for a career in companies like NVIDIA or AMD or even Intel, a sound understanding of assembly programming will be quite beneficial. Okay, so there are some jargons associated with assembly language programming, and one of them happens to be the instruction set architecture. So your instruction set architecture is defined as an interface between hardware and software. Think of it as a rule book that guides software to be executed on the hardware. You can also view it as a contract between the hardware designer and an assembly level programmer. So use it as a grammar book, essentially, and use it to communicate with the underlying hardware. That's what an instruction set architecture is all about. It's going to define all the different methods with which the programmer can perform different tasks. For example, how to specify arguments to a particular instruction, how to format memory addresses, and so on and so forth. There are different kinds of instruction set architecture out there. For example, Intel x86, you have Intel AMD x86-64, you have ARM, you have IBM PowerPC and MIPS, and they are all strikingly different, just like how C++ is different than Java, and how Java is different than Perl and PHP, and so on and so forth. However, if you were to pick up just one particular instruction set architecture, picking up all the others will be quite easy. I'm not saying it will be completely straightforward, but it will be very easy. Now, let me give you my personal example of how I learned an instruction set architecture, and then I acquired these ISAs as well. So the very first time when I programmed a processor using assembly was in the year 2006, when I was pursuing my undergraduate degree in instrumentation and control engineering. I was a sophomore then, and at that time, our curriculum did not require us to directly acquire all of these advanced ISAs, because as instrumentation engineers, we were responsible for working with smaller microcontrollers at that time. So the ISAs that we had to learn were not very complicated. So we learned the ISA of Intel's 8085 processor, which happened to be an 8-bit processor. And we wrote all the different kinds of programs such as bubble sort, insertion sort, etc., using simplified instructions. In fact, I even remember that I had written a routine just to perform division as well. So those were the days. However, by acquiring or by learning the ISA for 8085, I was able to acquire or learn the ISAs for Intel AMD x86-64 and Intel x86, which I used to teach undergraduates at Clemson University. And now I'm also able to understand how MIPS works because of my background from before, and I'm teaching you, or I'm going to teach you how to write programs in MIPS. So there you go. Learning one language makes learning the next one much easier. I'm not saying straightforward, but much easier. Now, the next question that may come in your head is why to use MIPS. The reason why we chose MIPS is because it is based on RISC architecture. It offers you a small set of instructions with which you can virtually accomplish a great deal of tasks. And MIPS is a famous architecture as well. In fact, there are a lot of textbooks that are using MIPS actively. And not only that, it also aligns with ECPE 173. Both Dr. Schaefer and I, we are actually working on advancing our curriculum for ECPE 170 and 173 by moving on from MIPS to ARM, because now I think it's time for us to move towards the ARM processor, because now they are more prevalent than the MIPS architecture is. Okay, so let's end this lecturette right here and call it as MIPS Motivation Lecturette. So in this lecture, we covered why computer scientists, computer engineers, and electrical engineers can greatly benefit by learning MIPS assembly. In our next lecturette, Lecturette 2, I'm going to discuss arithmetic instructions and branching instructions. So here's how our view is going to be with respect to our computer while learning MIPS. We are going to consider our our computer as a baby that does not know how to speak. And slowly and steadily, we are going to teach our computer one instruction at a time. So initially, we'll teach our computer how to perform or how to speak in terms of arithmetic instructions, add and subtract. So at that point, all that our computer can do will be just addition and subtraction. Then we'll add some more capabilities slowly and steadily. Then we are going to add some branching instructions for it to make for our computers to start making decisions. And then we are going to keep turning our level up by a notch one at a time. And we are going to deal with other instructions like how to access memory variables, how to call functions, how to return from functions. So that's how we are going to slowly and steadily teach our computer how to talk to a human. So we are going to end our lecturette right here. I hope you enjoyed this lecturette. As I mentioned before, you can always pause these lectures and or replay it over and over again if it doesn't make sense. For everything else, Dr. Schaefer and I are just one email away, or you can also meet us during our office hours via WebEx. So we'll end our lecturette right here.